Hello and welcome back. In Math 180, you learn about a more formal way of defining limits called the epsilon delta definition of the limit. And it turns out that sequences also have a sort of epsilon delta, or we'll say epsilon n definition of the limit of a sequence. So here it is. It says that a sequence a sub n converges to L if for every epsilon greater than 0 there is an integer big N such that for all little n past big N, so greater than big N, the difference between your terms and the limit, so a sub n minus L in absolute value, is less than epsilon. The visual looks something like this. Suppose we have a number line representing n, and then here's a sub n along our y-axis. So this is saying that we're going to get convergence to L. So the a sub n's values, the y values, are going to get closer and closer to L if for every epsilon, where epsilon represents a distance around, or a distance from L. So here I'm just representing this as L plus epsilon, L minus epsilon. So epsilon kind of represents this small distance from L, so that you end up with this little interval around L, a little tube as we're going to extend it out into to the right. So then this is saying that if for every epsilon, so here we've picked an epsilon, and we've this is kind of like the challenge, the epsilon challenge. We want to be this close to L. Well, if for every epsilon challenge like that, if we can find a big N, so if we can go far enough out in the sequence such that for all n, for all terms of the sequence that are going to be past that big N, the term values fall inside this epsilon tube, then we've satisfied the challenge. So, you know, before n, anything could happen. You could have your terms going like this, they could be inside, but then after n, they have to be getting, they have to stay inside the epsilon tube. So these are some dots representing terms of the sequence. N is which term you're looking at, 1, 2, 3, 4, and so on. And then the y values are the values of the terms themselves. So if it's always the case that no matter how small you might make epsilon, you can always go far enough out in the sequence, you can always find a big N, such that all the terms after it fit inside that epsilon tube, no matter how tiny it becomes, no matter how close to L it gets. Then in the limit, as you move to the right, eventually the terms are going to get as close as you want to the limit L. And in that case, you would say that the limit converges, the limit of the sequence converges to L. So in example 2, we're asked, does 1 over n converge or diverge? So in other words, we're thinking, what is the limit as n approaches infinity of 1 over n? Now we can think about this you know, in a purely numerical sense. Just think, what happens when n gets big? 1,000, 1,000,000, 1,000,000,000. You're going to get 1 over those numbers, so the limit of 1 over n should be 0. And this would say then that the sequence converges. It converges to 0. But if we were asked to prove that, you know, numerically is fine, but if we were asked to prove that by the definition of what this limit is, then we could say something like this. Here's the proof. It's in the pudding. Let epsilon be greater than 0. Give me any epsilon you want. Challenge me. Here's how I'm going to respond. I'm going to choose big N to be 1 over epsilon. Now, of course, that's kind of magical. It's like, why 1 over epsilon? Where'd you get that? Well, it just has to do with how the rest of the proof is going to go. So usually you wouldn't figure this out until partway through the proof. But here I'm just going to do it in one shot. So suppose I choose big N equals 1 over epsilon. So if epsilon is smaller, well, I'm going to have to make big N a little bit bigger. I'm going to have to go farther out in the sequence to find a place where all the terms are going to be epsilon close to L. Then for all little n bigger than big N, what we've got to show is that the distance between the terms of the sequence and L is less than epsilon. So the distance between the terms and L, we've got to show that that's less than epsilon. Well, in this case, the L that we're proposing is 0, and the terms are given by 1 over n. So this is 1 over n minus 0, which is absolute value of 1 over n, which is just going to be 1 over n. The absolute value bars can drop away since n is going to positive infinity. But then here, on the side, we're going to say that little n is bigger than big N, right? That's part of what we're assuming about little n, that we're looking at the little n's that are bigger than big N, right? We're looking at the terms that are past big N. And if you flip these fractions on each side, that's going to flip the inequality direction. So 1 over n is less than 1 over big N. So what we can say here is this is less than 1 over big N. But 1 over big N is going to be just epsilon, right? If n is 1 over epsilon, then 1 over big N would be equal to epsilon. So at the end here, we can write equals, in our tiny little space left, epsilon. So here we've shown that the distance between the terms and the limit L is, through all this work, less than epsilon. Given this choice of big N, we end up getting less than epsilon. And we can do this for any epsilon, no matter how small it is. We can find a big N, a term, such that all the terms after it are within epsilon of the limit L. So therefore, the limit as n approaches infinity of 1 over n is 0. Now, having proven this example, I'll have to say that in this class we're not going to be doing a lot of formal proofs. Mostly we just want to pull the concepts out of it. And also I just want to challenge you to take a glance at some of the deeper levels of calculus. After all, in Math 180 you cover the epsilon delta proof and those situations, those kind of problems. But here we're not going to dwell on it because we have lots of other things to think about. For example, example 3. What do you think about this sequence? So we're going to put proofs aside and just think about this sequence here. Does 1, negative 1, 1, negative 1, 1, negative 1, does that sequence converge or diverge? Does it get closer to any particular number? If you said it doesn't, or that it diverges, that would be correct. So this sequence diverges. It diverges because it's oscillating between negative 1 and 1. It's not really getting closer to any particular number. So there are really two main ways that a sequence can diverge. One is that it oscillates back and forth, and so it doesn't settle in on any particular number. Another way is if it blows up to infinity or goes down to negative infinity. Those are the three main ways that a sequence could diverge. Now, it says find a formula for the sequence, and if you think back to what was causing an alternating sign, so positive, negative, positive, negative, positive, negative, we can take that part of it and use it here. So if you can think about what a sub n would have to be based on the last video, if you came up with negative 1 to the n plus 1, then that would be correct. Or it would be at least a possibility. This would be a correct possibility. It's not the only correct answer, but notice that it is an answer because if you let n equals 1, then you get negative 1 to an even power. 1 plus 1 would be 2. That would be an even power. And so you'd end up with positive 1. And then every time n increases, the even and oddness of the exponent is switching. And so you're going to flip the sign to negative and then positive and then negative and then positive and so on. So this would be one way to do it. But it's not the only way. You could also instead write a sub n equals negative 1 to the n minus 1, right? If all that matters is that the exponent starts on an even power, then n minus 1 would do that trick as well. When n equals 1, when we want to get the first term, we would get 1 minus 1 for the exponent, which would be 0, and negative 1 to the 0, that would be positive 1. So that gets you started off on the correct sign as well. So there are lots of other variations of these. Another clever variation would be using something else that you know that oscillates around, and that's trig functions. Trig functions go back and forth between 1 and negative 1 if you hit them at the right places. I mean, they go through all the other values in between, but if you hit them at the right places, they're going to be 1 and negative 1 and 1 and negative 1 and so on. So for example, we could use cosine. That don't have to necessarily use cosine, but if you use cosine and you write cosine of pi times n minus 1, like that, then that's going to get you 1 and negative 1 and 1 negative 1. Every time n, so when n is equal to 1, you're going to get cosine 0, which is 1. When n is 2, you're going to get cosine pi, which is negative 1. And then every time you add 1 to n, you're increasing the inside part of cosine by pi and getting the next value, 1, negative 1, 1, negative 1, and so on. So that'd be another way of writing that sequence. And it would be an interesting way because you're writing the sequence using a continuous function. The negative 1 to the n minus 1, that's not a continuous function because this only works when n is an integer. But the cosine works when n is even not an integer. So just something interesting about that alternate version. Most of the time, though, we're going to be using negative 1 to the n plus 1 or n minus 1 or any variation like that. Now, example 4 asks you to find a formula for the nth terms of this sequence. Now, here we have a couple of things going on. We have alternating signs, positive, negative, positive, negative, positive, negative. Those we can handle. In fact, let's start writing this up. So I'm going to put those signs on the top of these fractions. So I'm going to think of it as negative 1 on the top, negative 1. And in fact, I'm going to write this 1 as 1 over 1 just to make it look like a fraction like all the other terms. So you're going to have positive 1, negative 1, positive 1, negative 1. We actually just did that in example 3. So I'm going to steal the answer from example 3 as the top of our fraction. So then on the bottoms of the fractions, we have 1, 4, 9, 16, 25. What do those look like to you? If you said those look like n squared, that would be correct. In fact, we detailed out what the sequence n squared looked like. So if you break it up into these parts, the numbers on the top of the fraction, the numbers on the bottom of the fraction, it helps to be able to write a formula for the nth term of the sequence. Now each sequence is different. They're going to have their own patterns, and they might take a little bit of work to find those patterns. But it's really good to practice finding these formulas so you can get a sense of what the patterns are like. Thanks for watching this video, and see you in the next one.